Hi everyone, welcome to this week of machine learning. In terms of logistics, there's two small things. We got the course evaluation feedback from you guys. Thanks a lot for all the helpful comments. We will discuss this a bit more in the Q&A session on Thursday. If you can make it, it would be great. Then what else was there? Yeah, in terms of exercises, we will take it a little bit more easy this week and the following ones, because you probably also want some more time to focus on the project so that you can take a bit more time on your project too, and please also use the exercise sessions to get some help from our assistants for these projects. All right, unsupervised learning was our topic. We did a lot of clustering last week. Today we will have a very smooth transition from clustering to another kind of generative model, which is a kind of a generalization of clustering, addressing two of the main shortcomings, namely that the clusters were only allowed to be spherical in k-means, so they always have to be a round shape. We cannot have other kinds of geometries of one of the groups. That's one shortcoming in k-means. The other shortcoming was that it was a hard assignment, so every data point is exactly from one cluster. And that's also something that can be relaxed and might be useful for some applications. For example, the one here. That's the motivation to study Gaussian mixture models, and that's what we're going to do today in this hour. And this I already said. These are the two downsides, and this is our main motivation. So what we're going to do is to deal with more general shapes. That's quite easy. So we're just going to use ellipses instead of spheres. And that, you can imagine, is going to be relatively easily achieved if we use Gaussians, which have a more general covariance matrix. So you know this from the definition of a Gaussian in several variables, that the Gaussian can be a sphere, but it can also be more interesting shape, so something like this here with some axes, and then in the spherical case you have that the covariance is just the identity, and then in the case, so the identity in d dimensions, and here we have that the covariance matrix sigma is something more general. So this is what a Gaussian is. Not much new here, but we're going to exploit this property. All right, and how to do this is to have this kind of mixture model, which is already defined here in the full expression. So what this is that it's very similar as the probabilistic model we had for k-means, right? We said that there are k groups, every group is a spherical Gaussian, and that's how our points are explained. That's exactly the same expression as we had in k-means, basically. So if we go back for 1 second, then yes, that's what we had here in k-means. Remember, the probability of all the data points together was this product over all points times the product over all groups, and then we only counted the guys which are actually assigned to their group. So here small n went from 1 to capital N, and then we had these two products of Gaussians. So same thing here. If we do Gaussian mixture model, that's exactly the same expression. The only difference here is on the right here, that this is now the more general. So okay, and again, let me clarify what the Z and K's are. So maybe it's easiest to write them as this identity matrix 0, 1. So to the n. So that's the very same as in k-means. We also use the same kind of assignment variables Z, assigning any point n to a cluster k. So the set n vector is in our k. All right, nothing new so far. And so keep this in mind, we're gonna use this again. And so what's interesting about this model is that it has kind of three kind of parameters. So this is set parameters, which is the assignment to clusters. This will be a soft assignment this time, we're gonna discuss this. And the other parameters are pretty standard. So the mu, that's the same as we had in k-means already, you know that. And then what's the only difference here is the sigma, which is now a spherical and not only, which is now a general ellipse, not only a sphere. Okay, that's a Gaussian mixture model. That's how you can generate data from this thing. So you generate one data point at a time. You go over the groups here, and that's it. Okay, so how does a soft assignment work? So instead of having a point n always assigned to the same cluster, which is like a hard assignment, here we can do a soft assignment by making that z a random variable. So if you are data point n, that means that sometimes you are assigned to cluster 1, sometimes you are assigned to cluster 2. So there is an element of chance that, or how likely are you going to be assigned to each of the clusters k. That's what is happening here. And to do this, we actually use a very simple multinomial distribution. So we just have weights which sum up to 1, and so these are called this pi k for every group k. You have an importance weight, and this describes how important is group k. So how big is group k? So and they have to sum up to 1 if you sum over the groups. Okay, but the point here is that now this is probabilistic, right? So the set assignment is still like a 0-1 vector, but what it actually is will depend on the randomness. So there is a random outcome here. So z can be k, and it can also be a different variable. And how often this happens is determined by these fixed numbers pi k, these weights or importance weight of the group. Okay, to summarize, what kind of parameters do we have here to describe our probability distribution? That's these three guys. So just important to think about the size. How complex is it to describe our model? So the mu guys are in. So what's that? These are the centers of each group. So like in k-means, it's the means. So every center lives in Rd, and how many centers do we have? We have k of them. Then the sigma guys, this is a matrix now. So for every group, we have this covariance matrix. So this is actually a very large number of parameters. We have, because one of these matrices is d squared, and then we also have k groups. And finally, these pi guys, that's not so much, so they are just this one per group, so r to the k. Okay, so that's how many parameters we need to describe our model. Don't forget that the pi's need to sum up to 1. And with that, we have our Gaussian mixture model defined. Now we just need to see what does that mean, and why does this lead to a more general model of soft assignment. Okay, so here is what happens. So why does this give you kind of a soft clustering? So the way this works is that you have the parameters which define your probability distribution. So these are on one hand the pi, and on the other hand the mu's and the sigma. Sigma is the covariances. And from the sigma and mu, you have what gets generated here are the x's, so the data points. So x1, x2, and up to how many data points do we have? We have capital N data points. That's so far so good. I mean, the data points they're just there. They're not assigned to groups yet. But where is my data? That's depending on the mu and the sigma. Okay, and then there is another thing coming into play, that every data point also has an assignment vector. Z1, Z2, and Zn. So these are all k vectors. And how are they generated? They're randomly generated from this multinomial distribution, which is determined by this fixed parameters pi. So again, trying to keep these colors. So that's the entire process how data is generated. So, okay, I forgot the connection, that if you have the labels generated, so where the group assignment is, then you actually have complete information to generate your data point, because then once you have which group it is assigned to, then you know which of the Gaussians it's coming from. So that's why the arrow here indicates that it's like conditioning on. So this is this graphical model kind of notation, or to make this kind of plot or schema, is that whenever the arrow means that, okay, this thing is already there, and now from this some random outcome is generated, so the z's are generated, and then from the z's I can generate the x from the respective Gaussian. All right, that's the illustration how the data generation works. So don't forget these assignment errors. They will be key, and they are random variables, and they're called the latent variables. Okay, so now we want to understand a bit more precisely what this means. So we want to formulate what is the whole likelihood of this model. So and that means exactly what we were just talking about, basically. The likelihood is what is the likelihood of getting this data X and getting this kind of cluster assignment if you have these particular parameters, so meaning the mu's and sigmas and the pi's. That's what we want to figure out now. And to do this, so this is actually not so hard. We will just use the definition of a Bayes rule, and this will help us to understand how this data is generated here. So let's see. So here, what we have here is so-called the joint probability. So it's x and z's together, and then the problem is we don't really see z, so it's not easily available. So we want to break this down so that we can get something like a likelihood. So we are caring only about the probability of x. We just don't know what z is, right? So you need to figure out what's the probability that you generate this particular x. So that's the kind of term we're interested in, and that is actually the likelihood. So this don't worry about the equation yet. For now, just I want you to understand that this is the likelihood, and this is then what we call the prior. And so this is just names, nothing has happened. But now, why is this actually the same thing as the joint here? So the joint probability, and so that's the first thing. Why are they the same? And why does this equality hold? And that's very simple. That's just Bayes' rule. And you are all very familiar with this, right? So probability of A and B is probability, so that's a joint. So if you have two random events happening, A and B, is probability of A conditioned on B, so it's conditioned that the B has happened, times the probability of B. So that's all we've done. It's pretty simple. And what we condition on here is actually the entire set of parameters. So we just happen to have three parameters here, and so your b is actually the z variable, and the blue stuff is what we condition on. So okay, so let me make this a little bit more precise. So so here's again, think of base formula. So, and actually you apply it conditioned onto some more stuff. So here is the condition on some additional events. So the additional events are the three parameters, right? And then the a and b, so this is just the x and z. Okay, so then to make this a little bit more clear, so the result you will get here is you get this also conditioned on all three parameters, pi, mu, and sigma. So that would be the entire conditioning, because that's what we have here. But we don't care about this, because if you look at the prior, then the z is only depending on the pi. It's not depending on where your means are or the covariance or anything. That's what we have here, because the z's are coming directly from the arrow on top. That's the only incoming arrow we have, so they're determined purely from the pi. And then if you look at the x's, once the z's are determined, then same thing there. They only depend on the mu's and the sigma. So if you want to ask what is x conditioned on all these parameters here, then you see they don't depend on the pi, they only depend on mu and sigma if the z's are already determined, right? So that's why I don't need to care about the mu's and sigmas here. Okay, so that means the blue stuff can be completely ignored, and we have applied Bayes' rule for a and b being the x and z. That's what we've done here. So nothing special much. And now what we're going to do in the next equation is we do the exact same thing as we done in k-means. So we will just write this differently. So here's probability that xn is generated from a Gaussian, but which Gaussian, right? And that's the one which is determined by z, the assignment. So that means that that's the arrow here, right? We need one particular z which decides you as a data point are now assigned to cluster 2. That is itself is a random event. But once you know what the random event z is, so then you know that this data point is assigned to cluster 2. And that's what this whole likelihood is. So you just write that it's the Gaussian which describes cluster K, and only that Gaussian will generate your xn. And how do you do that? You just again write this indicator variable. So because you condition on the assignment to be known, you know z and k is known, so only the cluster you're assigned to, that particular one will generate your x. And how it's generating? By a Gaussian of mu center mu k and covariance sigma k. Okay, so that's why we have gotten this product now, because we say all the assignment, only the ones you're actually assigned to, and the same for the pi's. So nothing special here. It's just that we have just plugged in the definition and used this notation using the assignment, and again Zn as always is a discrete variable. So it's a k vector 0 0 0. Okay, and yeah, that's it. So we have written down the entire expression now, and now we also understand a bit better that the xn is what we actually observe, and then the other guys said these are the latent variables. So the zns you actually see when you get a data set, right? Then that's what you get. You get the x's, and the z's we never see, right? That's kind of implicit. So we assume our data set has been generated from this Gaussian mixture model, but which sets? So that is depending on the random process, and these sets are not explicitly visible. So they're kind of the hidden latent variables. And if I stick to the color code, then these are the green guys. And what we also have is, of course, all the three parameters, the mu's and the covariance and the prior pi. Okay, so now if you get a data set, then you can ask, can I learn these blue parameters given only the x's? That's the same thing as we kind of did with k-means, right? So we got a data set x, it doesn't have any labels. Can you learn these most likely parameters which have then generated this data? And that's the same question we ask for k-means. We are going to ask it here because we have now written the likelihood. So given our x, what's the probability of that data x conditioned on these parameters? The only problem we have to deal with is the sets because they are kind of hidden and latent. The way we're going to deal with that is to study the so-called marginal likelihood. And to understand what that is, it's quite simple. So if you have a probability distribution, then you have I don't know, p of x and z, whatever, it can be p of x. So you just have two random variables. They might be related or not. And so what this is the joint probability, right? That both of them happen together. And then what I want to talk about now is the marginal of that joint probability. And that's also something very simple. That's just the probability of x. And what is this? So, because I can say I do not know what z is, therefore I will marginalize over z. That's what's happening here. And what that means is just that of all possible outcomes that z can have, I will just sum them all up and weight them with the corresponding probability. So it's a sum of everything that z can be. So to keep things simple, I will say that z can only be k possible things, so it's a discrete random variables, but of course you can define marginals for any random variables. Then you would also have a maybe integral. If z can have any values you want, then we just integrate over all these values. But here we just sum the probabilities of x. That's just by definition, it's a probability that of all combinations of x and z, of this particular x with all possible z's. That's just the most natural thing, like what is probability of x? You're like flipping two coins, right? And so what's the probability of this? Just the first coin. You just sum up of whatever the things can happen to the second coin. If you again use a base on that, you don't have to, but you can do that. Then you get something which is very similar to what we had. So x given z times the probability of z okay, and that thing in our case that was kind of the prior, so this was the pi k. Okay, this is what the marginal is, and we're gonna do this in our case now. It's gonna help us to get what we want. What we want is probability of the data, and what we want to overcome is that this set here is what we don't know, and that's how we're gonna do it, by just marginalizing over it. Okay, yeah, and if you want to to be more precise, then let's say this is what we discussed here. We applied to xn, so everything has n here. We do this for one data point, and then later we're gonna do it for all the data points together. So okay, but if you do this for one data point, then this is what you're gonna get, and that thing is called the marginal likelihood. So because likelihood before likelihood with standard way, it's just x and z condition on the parameters, and now why is it called marginal? It's because the z has disappeared. That's the only reason. So, okay, so parameters, they're all collected into this theta. That's just here, it's just a notation thing, right? We just call this theta all three guys together to just group them into one big array, give them a new name, theta. And so let's see what we summarize a bit what we have. The original likelihood was probability of x xn and so xn and zn conditioned on the parameters. That is the likelihood, the standard one. And then the one we have here is a special likelihood, is the one where z has disappeared, which is called the marginal likelihood. So that's the expression we have here, and it's very easy to check this computation. Right? So please have a look. If you have 1 minute, then you see the definition we had before of the joint thing, so, or of the likelihood here. That was what we had on this slide, right? And now you will just sum this up over all the things that z can be. So you marginalize out z, and what you then get is this. So, and why is that? That's because probability of z being k is just pi k by definition. So these guys, that's kind of crucial, and then you will get this equality. Okay, why is this good? Because this is something we can actually observe. We observe the x, and from that, using this marginal likelihood, we can estimate what are the correct parameters, the mu, sigma, and pi. Whereas if you talk about x and z, so we don't see the z, we don't see the assignment of every point to a cluster. We don't see that. We only see all the points mixed, right? This is unsupervised learning. We don't see any assignment, right? That's our job to make the assignments and find the clusters. So here is how we can do that, by defining a likelihood which only explains x, and then finding the parameters using that. This is nice. This is also more statistically efficient. In what sense do I mean that? It's just you will have much less parameters you need to determine. So because there are many of these z guys, so z has their n times k values, or okay, if you have, it's a 0, 1 vector, right? But let's say for every data point you have to find one of these z vectors, so there are at least n of these vectors. There are a lot of them, and it's not so easy to estimate all of them from data. And we also need to estimate the mu case, the sigma case, and the pi case. So this is as before, k times t squared. Okay. So there's quite a bunch of things to estimate, but the n is by far the largest number. You have millions or billions of data points, but you don't have millions of clusters usually. So n is very big, and therefore it's a very good idea to solve this more well-behaved problem, which is only defined on the sigma on the theta parameters, not on the z. So that's the marginal likelihood, and this is a very helpful concept and makes our problem more tractable. Why do we care about likelihood anyway? So we want to use this to, now we have the expression explaining how the data is generated, and now we use this to, given the data, find the parameters which mix this data most likely. That's called the maximum likelihood principle. So we just take this nice expression that we derived and we plug in the x that we observed, right? And now we're gonna maximize this expression over the parameters to find the most likely parameters. That is what maximum likelihood is. So that's what is happening here. So standard likelihood as before, maximizing the likelihood, finding the most likely parameters, explaining your data x. So yeah, so here are the parameters theta, and again this has three parts. It has the mu part, the sigma part, mu, sigma, and pi. These three kind of parameters, they're all collected in the theta. And what we have is we have data x. So x we observe, and now we want to find the theta which maximizes this. Okay, so why is this sum of log of sum? That's very strange. So what we do here is, so this is something we have to actually compute to convince ourselves that what does this have to do with what we just computed before, right, with the likelihood we derived here. So we know that this likelihood of one data point given parameters is a sum over this k, and the likelihood of the whole data set is what we want here. So let me write this here. So what our goal is to find the probability of all the x. So that's just capital X usually. Given parameter theta, that's what we want to compute. And of course, every data point follows the same generation process. So this is just a product of the probability of each of the n data points. So P of x n given theta. Okay, but now this expression is exactly what we had before. So we had derived this here in the marginal likelihood, probability of 1 point given data. That's exactly what we need, and this is the sum over the groups. So this one data point, its probability is actually pi k times the normal distribution of mu k sigma k. Sorry. Xn from a normal distribution which has the mean mu k and variance sigma k. That is what we have computed before, how to generate one data point. Okay, and now it's a bit strange. So now we have a product of a sum, and that is a bit nasty. So what happens now is that we say we don't want this. We don't want products. We prefer to deal with sums. The easiest way to do that is just to put a log around everything, and then what you get, so is the log of this product is the sum of the logs, sum over n 1 to n of the log of this thing. And what's this thing again? That's the sum over the k. Okay, and that's the expression we have here. So we have convinced ourselves that the strange expression here is actually the log likelihood. Okay, now you have your whole machinery. Now you have Gaussian mixture model. By the way, that's why it's called a Gaussian mixture model, right? Because it's Gaussian, and these are the mixture weights. The pi's are the mixture weights, which are mixing the several Gaussians with this weight pi. All right, and to find the most likely parameters, we just need to solve this maximization. But this looks a bit nasty, right? So sum of log of sum, that is quite a difficult expression. So, and it truly is a challenging problem, because we will see in a second that it also generalizes k-means. That was always the intuition. But this one is an even harder problem. Why is it hard? So, because, yeah, it turns out that this problem is not convex. It's also not identifiable, means the solution is not unique. So, and it's also not bounded. So it's quite a nasty optimization problem. Let's take a second to understand why that's the case. So it's a non-convex. There are several ways you can convince yourself, but basically it's just not, there's no reason. It can be convex. You can look at the definition of the Gaussian and then solving that for the mu's alone might be okay, but here we have the Gaussian, need to solve it for both mu's and sigma, because we are maximizing over all these guys, mu, sigma, and pi, and they get multiplied with each other. Therefore, this is a very non-convex problem. Second, it has non-unique optima. So, so several optima. Why is that? Do you see that? The reason it has some, one reason it has some non-unique optima is once you have one optimum, you can get other optima by just adding, permuting the groups, just giving different names to the groups. So the value of your whole optimization problem will stay exactly the same if you change the names of the group. And that is something which is an allowed transformation, so permutation. Permutation of k, the set k. So if you go from k to k prime, then everything changes, right? So pi k goes to k prime and so on. So the mu's change, but the value always stays the same. So the value of your optimization problem. So nothing has changed if you just give them different names. So have the groups in different order, then the value stays the same. But now you have a completely different solution. The parameters which were, so these guys were optimal, but now you change things around and copy them into another position of k, and you say you have the same value, so you also have an optimal value at a very different optimum. So that's why you have a non-unique optimum. So these parameters can be permuted without changing the objective. I mean, there might be other optimum. I'm not claiming this is all you can do, but this is one thing you can do, which is already giving you non-unique optima. Third, it's unbounded. And what I mean by that is that if you walk into some strange directions in a bad neighborhood, so to say, then things will explode. So the value of your objective might go to infinity. That's what I claim here. And why is that? So anyway, this is the whole function L. This is like our cost function, right? Now here, this is the likelihood function. I claim that L goes to infinity. When does this happen? So one easy case when this can happen is when you just have the covariances becoming very small in diameter. So it doesn't matter if they're round or elliptical, but what matters here is that if they become very concentrated around a small region here. So here is your mu k, and the diameter here is the sigma. So that's kind of describing how wide is your Gaussian, right? So by the way, this plot here, it just means that we have two Gaussians. So here is the Gaussian from the first one, and so you have a Gaussian mixture model of two Gaussians. They are mixed. The first Gaussian gives you this kind of flat peak here. So far, so good. The second Gaussian has a more spiked peak. And what I mean here, what I just want to discuss here is that these Gaussians can become even more spiked. And that happens if you use covariances which are scaled with a small width, and that's what we call sigma here. So if you make this width very small, that's something you can do, then this Gaussian becomes very narrow, which is like in the picture here. And then when you make this sigma go to 0, then you will have this cost function here, the likelihood, gonna explode to infinity. And that's why is that? That's also something you can convince yourself quite easily from the definition of the Gaussian and of this likelihood function. That's actually we have in the lab. Next week we have a small exercise for you to convince yourself that this happens. Okay, so this is just to illustrate that this problem to find the best parameters to explain your data is not so easy in Gaussian mixture models, even if it's quite a simple generative model, right? So generative in the sense that you get this parameter theta, you generate data x. Okay, that's what Gaussian mixture models are, and in the next part we're gonna give you a good algorithm still to solve this, and it's gonna be an approximation algorithm. It's gonna be very efficient. It's also gonna be very similar to the k-means algorithm, because this here generalizes k-means, which is also not hard to see. And then the algorithm we're gonna discuss is gonna be giving you a very good approximation to these maximum likelihood parameters here. So, by the way, why does this generalize k-mean? That is also quite easy if you look at the definition here. So even at the very beginning you saw that. So if you you can get k-means when you just have the sigma matrices become the identity. So k-means is a special case of this. K-means if sigma k is the identity. It's a very important special case, and then we will see this next part when we apply the more general algorithm here for the special case of no covariances. Then we will get back the k-means. But that's for the next part, and maybe let's take a 1 minute break.